Although it seems as if making a pizza is an easy process, there are many thermodynamic properties involved that go on behind the scenes. In the next few minutes, we will take the time to explain these processes for you.
The first step in any baking process is mixing your initial ingredients. The thermodynamic property that comes to mind is entropy. Entropy can be defined as the capacity for change of a system. If the state of a system is changed but the entropy is not changed, then the process is called reversible. However, in our process, entropy is changed, therefore our process is not reversible. The second law of thermodynamics basically states that everything moves towards equilibrium because of entropy. Since entropy is the driving force behind equilibrium, this means that our system and the universe are constantly moving towards a less dynamic state.
Our ingredients are salt, sugar, yeast, flour, milk, and oil. When mixing ingredients, entropy drives the process to equilibrium, which results in dough.
Look at me pour this water. Entropy, 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 entropy. Entropy, 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 entropy. Entropy. That's a mighty fine looking dough. Oh my God, I'm making a pizza. Equilibrium.
We will say that there are only 3 parts of a pizza. The lowest layer is made of a yeast flour dough, the second layer is largely tomato paste, and the top layer is cheese. Trace materials such as oregano, basil, and pepper are also present in small amounts, but we'll ignore these. The lowest layer is called the crust. The dough of the crust bakes into bread, which is a low water content material with a large number of non-connecting air spaces. The crust becomes an excellent insulator because of the unconnected air spaces throughout. Surface area is an important part in cooking. The greater the area in contact, the more the time it will take to transfer heat. So if you use a flat bottom utensil to heat, you know it's going to take more time, but remember your food will be more evenly cooked. We spread the dough out not only to create more pieces, but also to create more surface area so the pizza can cook more thoroughly. The second layer is the sauce. The tomato paste of the sauce dehydrates. Tomato paste has a high heat capacity and a low conductance. It serves as a buffer between the insulating crust and the cheese. The top layer of a pizza is the cheese. The cheese undergoes a complex series of transitions involving protein denaturation and lipid rearrangement from the liquid crystals to more disordered states. In other words, it melts. The transition results in a high heat capacity for the melted cheese. The pizza cools quickly due to the high heat capacity of cheese. Oh yeah, knead it. Knead that dough. Spread it across the sheet. Knead it. Oh yeah. There you go. Get them corners. Get them. Spread it evenly. Knead it. Knead that dough. Almost there. Get some of that surface area. Oh yeah. Cook it evenly. Surface area. Oh yeah. Oh yeah.
When we supply heat energy from the oven to the pizza, some of the heat is converted into bond energy as water evaporates and chemical reactions occur. But most of the heat energy causes a rise in temperature in the cheese and sauce proportional to the quantity of heat energy supplied. This can be calculated by Q equals C times M times delta T. Q is the quantity of heat supplied, and the temperature rises from the initial temperature to the final temperature, where the initial temperature is room temperature and the final temperature is the temperature of the oven. If we add heat to any homogeneous sample of matter of variable mass, say the cheese to the pizza, the quantity of heat needed to raise its temperature is proportional to the mass as well as to the rise in temperature. This means that the constant, C, is the heat capacity per unit mass. It is called the specific heat capacity, or sometimes the specific heat, where the word specific here means per unit mass. So have you ever wondered why pizza burns the roof of your mouth but not your tongue? It is due to the cheese having a higher heat capacity than the crust, We can prove this by calculating how much heat is transferred to the roof of your mouth by 15 grams of mozzarella cheese when it cools from 140 degrees Celsius to body temperature, which is approximately 37 degrees Celsius. Given that the specific heat capacity of mozzarella is 3.7 joules per Kelvin gram, and calculating how much heat is transferred for the same mass of bread at the same temperature with heat capacity at 1.7 joules per Kelvin gram, using the equation Q equals C times M times delta T, we found that the cheese layer would transfer approximately 5.7 kilojoules of heat, and the crust only transfers 2.6 kilojoules of heat.
Here's the right way to cook the dough. Oh my gosh, guys, don't look at my butt. And the wrong way to cook the dough. Obviously, I've never been good with tight spaces. Is my thong showing? Ta-da!
The type of oven we use to produce heat did so through convection. Convection is when heat is carried to the food by a fluid such as air, water, or oil. Coils in our oven produce convection by producing heat that will rise through the air in the oven. Heat is also transferred to the pizza by other methods. The pizza pan absorbs heat and transfers heat through conduction where it touches the crust. The exterior of the food absorbs heat and produces conduction through the heat moving to the center of the food. And the walls of the oven reflects most of the heat back to the pizza. We will pretend that our oven is a perfectly closed system so we can calculate work of the oven. A closed system can be defined as an isolated system that has no interactions with its external surroundings. Our system is not a perfectly closed system due to the oven letting out small amounts of heat to its surroundings.
Saucy. This is going to be one tasty high heat capacity buffer layer, I can sure tell. Look at me and my man glove. All floury and everything. Spread that buffer layer. Yeah, that's right. Oh, look, I made a penguin. Wow, that's really cool.
Cheese! High heat capacity, yummy melted cheese! Ready to undergo some protein denaturation? In other words, I want to melt! I love me some cheese! Yeah! While cooking, the thermodynamic property of entropy once again makes its appearance. Since any two objects at different temperatures brought together will come to equilibrium at the same temperature, due to the increased entropy for the spontaneous change to force the heat to move in the opposite direction requires some external force, work, to make up for the change in entropy. When cooking our pizza, we had to supply work to make up for the change in entropy. Since we said this process is a perfectly closed system and there is no heat transfer from the system to the surroundings, we determined our process to be an adiabatic process. Work in an adiabatic process is calculated by work equals heat capacity times the change in temperature. We used 113.5 grams of mozzarella, 427 grams of dough, and 150 grams of sauce. Provided were the specific heat capacity of mozzarella at 3.7 joules per Kelvin grams, dough at 1.7 joules per Kelvin gram, sauce at 1.88 joules per Kelvin gram, and our temperatures go from 25 degrees Celsius to 246.1 degrees Celsius. Our calculations consisted of finding the work required from each substance, then adding them up to produce an amount of work needed. We found our total work needed for this temperature change of all substances combined to be 333.84 kilojoules.
Almighty convection
Convection
of apartment 12.
Of apartment 12.
I grant you the
pies.
gift of one epic filled pizza pie and one delicious pizza pie. Please do your best. Make them work. Yummy. Not so yummy. Ooh, toasty. A, please.